Hello students, we're going to talk about the bloodstream biochemistry, and there's a good handout also on module 2 regarding this with a lot of nice pictures. I'll show you it at the end of our discussion. I also began this discussion in the Zoom that we did on Tuesday. So this is really important, and it's going to be something that we're going to look at also when we talk about hemoglobin. And that is in chapter 4. For right now, what we want to consider is that if we have a cell and we're converting glucose to CO2 and water via cellular respiration. Now, this is a topic that we look at in a lot of depth in the semester. So we spend weeks on metabolism. But for right now, what we want to consider is that the CO2 is a waste product, and it's going to go into the bloodstream. And the CO2 is going to react with water to form carbonic acid. Now, I introduced Le Chatelier's principle to you, and now we can really put it to an application that in the tissues where you have cellular respiration, brain, muscles, I think now is a good time to tell you that in biochemistry, we focus a lot on the brain, on muscles and liver cells. There's certain organs that are kind of part of our discussion. And as we continue on in the course, you're going to see this over and over again. So let's right now say muscles, that you're doing muscle contraction, you're going to run. And so your muscles store glucose in a storage molecule called glycogen, and it's going to pull from that to generate ATP for muscle contraction. As a result of that, you're going to see a higher amount of CO2. So I'm going to switch colors. So you're going to have a higher partial pressure of CO2 in the tissues, such as the muscle cells. And what's that going to do is that's going to raise the pressure of CO2. And Le Chatelier says that when you have a system in equilibrium, if you stress it, it's going to move away from what you've added. So this is Le Chatelier's principle. That when you add, in this case, we could see it as a reactant, it's going to shift away from the added, I guess we call it a stress, right? We're adding that. Now, when we talk about shifting, shift will mean react. So it means it's going to make more product. In this case, that's carbonic acid. And so now what we want to do is we want to remember what an acid does in water. And that is that it ionizes. And the acid will ionize. Okay, and that's in an equilibrium. You know, we know the equilibrium expressions for these. So if I write the Kc value for the first reaction, it would be carbonic acid over CO2. Okay, and then for the second one here, our Ka would equal H3O plus bicarbonate over carbonic acid. No water liquid, right? Okay, so in the tissues then, when the partial pressure of CO2 increases, you make more carbonic acid, and then more of that is going to ionize because now you've increased the amount of carbonic acid. And again, that's like adding a reactant for the second reaction. That's going to shift away from the added stress. And so in the tissues, these reactions shift right. Okay, and here's the thing though, is that the body wants to stay at a certain pH. And the pH, physiological pH, is 7.4. Okay, so that's the pH that needs to be maintained. Interestingly enough, we can use our Henderson-Hasselbalch equation. And why can I use this equation? Is because we have a weak acid and we have its conjugate base. So this is a buffer system. Okay, so the bloodstream is buffered with bicarbonate and carbonic acid as our main players. Now, if I look up the pKa of carbonic acid, or Ka, this is part of a worksheet that I've assigned. So I'm going to grab my book, kind of late in the day, so I don't want to get the wrong number to you guys. So I'm going to look up the Ka of carbonic acid. The Ka for the first reaction is 4.3 times 10 to the negative 7. And if I take the pKa, 4.3, negative 7, negative log of that. So it's 6.36. Okay, so what I will do, and it's just kind of a side note, and I'll put it over here. This is a side note, is that I can solve for the ratio of base to weak acid that we need to maintain a pH of 7.4. So it's just to give you an idea of that ratio. I won't ask you to do this. This is just more to kind of put things in perspective, because we talked a lot about how this ratio determines where our pH lands relative to pKa. So let me just give you kind of that information. Should be 11, yeah. So in other words, this ratio of bicarbonate to carbonic acid to maintain physiological pH is 11:1. Okay, and that needs to be maintained because our bodies need to stay at a relatively constant pH. When you see, it can't shift very much in either direction, either very acidic or very basic, before we can go into a coma and or die. So, so let's continue on with our discussion and with that. So let's say you are jogging. The pressure of carbon dioxide is increasing in your tissues, in your muscles. That's increasing the amount of CO2 in the bloodstream. That shifts these equations right. So during exercise then, what will happen is we'll see an increase in H3O+. Okay, that means that your bloodstream's becoming more acidic. Now, to keep this 7.4, our pH, the ratio has to stay around 11:1, but now you're messing that up. And if the pH starts to drop, which it will, then you can run the risk of having an issue. But the last time you went jogging, you didn't go into a coma, you didn't pass away, you didn't die. And that's because the blood will compensate for more acidity because the bloodstream ends up in the lungs. So in the lungs, and I'm going to erase my cell, my very poor drawing of a cell. In the lungs, what'll happen, and if it's okay, I'll write a different color. In the lungs, the CO2, right, we exhale. Now, what Le Chatelier's principle, and can I abbreviate that as LCP, Le Chatelier's principle, I'll highlight that so when you watch, there you go, okay. What Le Chatelier says is that if you remove a product or reactant, the reaction will shift to replace it. So as we exhale, then the reaction shown here is going to shift towards trying to replace that CO2. So in the lungs, these reactions shift left. That's going to pull this reaction to shift left. And what's that going to do is that's going to bring down the amount of H3O plus to maintain this important ratio that we need to keep the pH at around 7.4. So our breathing out, exhaling CO2, that is so important because it's reducing our blood acidity. It's making it less acidic. So in a scenario all day long then, as we are walking around and we're doing cellular respiration, these reactions are shifting to the right in the tissue, shifting to the left in the lungs. When we have an exercise scenario, we put a stress on this buffer system. So the carbonic acid and bicarbonates, our buffer system, we put a stress on it because we make more H3O plus when we exercise. But we have to get rid of that. And the way we do that is by exhaling more CO2. So there are other systems, and this is something that the readings will talk to you about. And then I just ask you a few questions. There's another there's another buffer system in the body, in the kidneys. And in the kidneys, the buffer system is one that we looked at before. It's this H2PO4 minus, HPO4 2 minus. And that's because the pKa of that system is 7.21. So you see how it's close to our physiological pH. So it's a good buffer. And I'm just going to confirm that number just so that I don't confuse you if I'm not remembering it correctly. Oops, sorry. So I'm taking the negative log of 6.2 to the negative 8. So 7.21, yes. Okay, that's another buffer system that's in the kidneys that helps regulate blood pH. And then in chapter 4, we're going to talk about how hemoglobin plays a role. Okay, so imagine then that you have the scenario of exercise where you increase the amount of H3O plus in the blood. Then we compensate for that by exhaling more CO2. Other acids that can play a role would be like lactic acid when you have a very intense muscle contraction and you don't have a lot of oxygen around, you can make lactic acid. That would also factor into here and increase the acidity level. There can be diseases, metabolic processes in the body that also increase acid level. And that our main way of compensating for that is through our breathing. Okay. Now let's think of hyperventilation. Like if we're exhaling because we're scared or in a flight or fight scenario, or we're anxious, so we're breathing out a lot of CO2, then what will that do? Take a moment to think about it. Exhaling too much CO2 is going to make our bloodstream less acidic, more basic, right? Because we're shifting too much to the left. And one of the ways that we can limit that is by taking a paper bag and holding it to our face. What we're trying to do there is keep that CO2 in our system so that we don't shift this too far to the left. Other scenarios would be is that if in let's say, I think I mentioned this in the other Zoom discussion, is I know my dad was in the hospital at one point. His bloodstream became way too acidic. He was sick and diabetic, and so it kind of put a stress on all this. And so they had to inject him with bicarbonate. And do you see how that is going to be adding a base to neutralize excess acidity levels in the blood? Okay, so this is a super important discussion, and it's one that we'll build upon as we keep moving forward and then eventually tie hemoglobin into all this. So I'd really like you to learn this really well, and for sure it'll be on your first exam. Let me also then, I'm going to stop this PowerPoint. And then I want to show you on the internet. Here is the article that I've linked. This is Blood, Sweat, and Buffers, pH Regulation During Exercise. It's from Washington University, Department of Chemistry. It's a really great article. So I would read it and I would kind of look at all the great pictures that it has. It has a lot nicer pictures than the one I've drawn. Here's our carbonic acid bicarbonate buffer. It goes through the equilibrium, the K values. So I think you can really read this now based on everything that we've talked about. And, you know, it's just another reference, you know, regarding this particular buffer. Interestingly enough, here's some titration type curves that we're looking at. It's in that style, which here shows the pKa. So I think everything we've been talking about over the last few weeks, that it kind of pulls together in this article. So if you read it and then you can answer the worksheet, I think you'll get a really good feel for how we can apply Le Chatelier's principles, buffers to a biological system.